Today I'd like to talk about prime factorization. So in order to talk about prime factorization, we need to first understand what the word prime means and what the word factor means. And so the word prime, a prime number is a number greater than 1 that is only divisible by 1 in itself. So for instance, a number greater than 1, so 0 and 1 don't count in the definition, so the next biggest number that we could start with is 2. Okay, so let's look at 2. Is 2 a prime number or not? The definition is a number greater than 1, all right, it's greater than 1, that is only divisible by 1. Well, 1 goes into 2 evenly, perfect, and itself, 2 goes into 2. Great, and there's no other numbers that go into 2 a whole amount of times, meaning with no remainder. So 2 is prime. 2 is a prime number. In fact, 2 is the only even prime number, because if you think of the next even number, 4, 4 is not prime because it's divisible by 2. Any even number is divisible by 2. Because even numbers, except 2, are divisible by 1, itself, and 2, that makes it not a prime number because prime numbers are only divisible by 1 in itself. Okay, so even numbers, not prime. 3 is 3 prime. 3 is greater than 1. It's only divisible by 1 and 3. Okay, so 3 is prime, 4 is not, 5 is prime, 7 is prime, 8 is not prime, it's even. 9 is not prime either because 9 is divisible by 3. So how about 10? That's even 11. 11 is prime. 13 is prime. 15, not prime. It's divisible by 3. And also 5. Numbers that are not prime, so not prime numbers, they have a name, and those are composite. Composite numbers. Composite numbers are composed of factors other than 1 in itself, so that's why they're called composite. Okay, so that's what prime numbers are. Factorization. What does factor mean? Factor is a number that goes into a larger number an amount of times, a whole amount of times without any remainder. So for instance, 6 has factors 1 and 6, also 2 and 3. So 2 is a factor of 6 because 2 goes into 6 3 times exactly with no remainder. So 2 is a factor of 6. 3 goes into 6 twice with no remainders. How about 10? 5 is a factor of 10 because 5 goes into 10 twice with no remainders. You could just pick any number. 18. 9 is a factor that goes into 18, an even number of times, meaning a whole amount of times with no remainders. So that's what factors are. So when we're looking at something that's called prime factorization, we're looking for factors that are prime. So let's give an example. So let's take the number 10. Let's say we try to break 10 into its factors that are prime. That's called prime factorization. So we would say, oh, well, 10 is 2 times 5. So let's look at 2. Is 2 a prime number? Yes, as we said before. Is 5 prime? Yes, as we said before. So we have broken 10 into all of its factors and making sure that all of those factors are prime. So we'll circle those, 2 and 5, and there you have. 2 and 5 are the prime factor. We have broken 10 down into its prime factors. Let's do another one. You can break any number that's not prime into smaller factors. So how about let's say 50? So you could think of 50 as 5 times 10. You could think of it as 25 times 2. The great thing about do you see it's turning out to be like a tree? The great thing about these factor trees is that you can start any way you like. You'll all end up at the same spot at the end, no matter how you start. So let's say we chose 25 times 2. Whenever I see a prime number, I want to stop my analysis on this branch and circle it. So I know that I can't break 2 down into any further smaller factors. 25 I can. 25 is a composite number. because there are factors inside 25. So it turns out that 5 times 5 is 25. Now 5 themselves are prime, so I'll circle those. So breaking 50 down into its prime factors is 5 times 5 times 2. Okay, so I could write 5 times 5 times 2 equals 50. I want to show you that even if I had started out with another idea of how 50 could first be broken down into, let's say I did do 5 times 10. Okay, let me circle 5 because 5 is prime, and so I'm not going to continue this branch anymore. I'm done with that branch. 10 is composite. I could break that down into factors like 2 times 5. Now 2 prime, 5 is prime. So this is 5 times 5 times 2. So this would be 5 times 5 times 2 equals 50. Do you see that I found the exact same factors no matter how I started? Doesn't matter how you start, we will finish with all the same prime factors. So that's how you carry out prime factorization. And the numbers could just keep getting bigger and bigger as well. So I'm gonna do one more example and then I'll let you try a few examples. So let's do something like, how about 90? Let's do 90. So let's break 90 down into its prime factors. So there's lots of ways to start this. I could see that 3 and 30, 3 times 30 is 90, so I could start with that. 3 is prime, so I'm going to circle it right away. 30, there are factors of 30, so 30 is composite. There's more branches that we can make in this tree. So let's say 2 times 15. Okay, 2 times 15, I circle the 2. Now 15 could be broken into 3 times 5. Now 3 and 5 are prime, so I'm going to stop. So my answer, like, how does my answer look? My answer will look like this. 2 times 3 times 3 times 5. This is the prime factorization of 90. Now, I personally like to start with the smallest factors and kind of list them out. If you want to rearrange these, if you wanted to say 3 times 2 times 3 times 5, that's fine as well. I'm just saying traditionally we start from the smallest factors and move on up. So either of these are fine, but I would traditionally do that as a standard form. All right, so I'll give you a chance to do some prime factorization.